Nonlinear Models 2.8 Introduction. We finish our discussion of single first-order differential equations by examining some nonlinear mathematical models. Population dynamics. If T denotes the size of a population at time t, the model for exponential growth begins with the assumption that dp divided by dt equals kp, both p's capital, for some k greater than 0. In this model, the relative or specific growth rate defined by d capital P divided by dt divided by capital P is assumed to be a constant k. True cases of exponential growth over long periods of time are hard to find because the limited resources of the environment will at some time exert restrictions on the growth of a population. Thus, one can be expected to decrease as capital P increases in size. The assumption that the rate at which a population grows or declines is dependent only on the number present and not on any time-dependent mechanisms such as seasonal phenomena can be stated as d capital P divided by dt divided by p capital equals f capital P, or d capital P divided by dt equals capital P f capital P. D capital P divided by dt equals capital P f capital P. The differential equation in 2, which is widely assumed in models of animal populations, is called the density-dependent hypothesis. Logistic equation. Suppose an environment is capable of sustaining no more than a fixed number of k individuals in its population. The quantity k is called the carrying capacity of the environment. Hence, for the function f in 2, we have f capital K equals 0, and we simply let f 0 equal r. Figure 2.8.1 shows three functions f that satisfy these two conditions. The simplest assumption that we can make is that f capital P is linear, that is f capital P equals C1 capital P plus C2. If we use the conditions f0 equals r and f capital K equals 0, we find, in turn, C2 equals R, C1 equals negative R divided by capital K. And so F takes on the form F capital P equals R minus R divided by capital K capital P multiplied by R divided by capital K. Equation 2 becomes D capital P divided by dt equals capital P, R multiplied by capital P minus R divided by capital K capital P in parentheses. Relabeling constants A equals R and B equals R divided by capital K, the nonlinear equation 3 is the same as D capital P divided by dt equals capital P A minus B capital P in parentheses. Around 1840, the Belgian mathematician biologist P.F. Verhulst was concerned with mathematical models for predicting the human population of various countries. One of the equations he studied was 4, where A is greater than 0, B is greater than 0. Equation 4 came to be known as the logistic equation, and its solution is called the logistic function. The graph of a logistic function is called a logistic curve. The linear differential equation d capital P divided by dt equals k capital P does not provide a very accurate model for population when the population itself is very large. Overcrowded conditions with the resulting detrimental effects on the environment, such as pollution and excessive and competitive demands for food and fuel, can have an inhibiting effect on population growth. As we shall now see, a solution of 4 that satisfies an initial condition P0 equals P0, where 0 is less than P0 is less than A divided by B, is bounded as T to infinity. If we rewrite 4 as D capital capital P divided by dt equals A capital P minus B capital P squared, the nonlinear term minus BP squared, B is greater than 0, can be interpreted as an inhibition or competition term. Also, in most applications, the positive constant A is much larger than constant B. Also, in most applications, the positive constant A is much larger than the constant B. Logistic curves have proven to be quite accurate in predicting the growth patterns in a limited space of certain types of bacteria, protozoa, water fleas, Daphnia, and fruit flies, Drosophila. Nonlinear models.